Hello everyone, welcome to our session. We're going to get started. First off, I want to mention, because we don't have the slide there, after the talk, please, if you could fill out the survey, it helps us a lot. But yeah, we're going to talk today about real-time crypto data intelligence at scale. I am Matthew Moorcroft. I am part of Databricks. I work as a specialist solutions architect, primarily focused on data engineering and streaming. And basically, this is going to be a little bit of a journey on the partnership that Elliptic and Databricks have over the past 2 years, and actually how we scaled this platform over time. You'll see some mistakes we made along the way and how we improved them. But yeah, excited to talk about it. Yep.
Thanks, Matthew. Hello, everyone. My name is Ferran Cabezas, and today, as Matthew said, we're going to be talking about the evolution of the data platform and how we have built a real-time platform. So the agenda for today, we're going to first talking about Elliptic, the history of it. We're going to be talking about Databricks components that have enabled user-facing analytics. We're going to be explaining what is user-facing analytics. We're going to be touching about optimizing streaming jobs, best practices, and key takeaways. So to start with, what is Elliptic? At Elliptic, we help crypto businesses, financial institutions, and law enforcement agencies to fight financial crime in crypto space. And just to give an example of that and show the products we have, so this is the risk management products that we have. And essentially, these allow us to screen an address or a transaction into a product. And then, essentially, with some risk rules that the customers are able to configure, we provide like a risk score, essentially, right? And we provide that on the sort of funds and the destination of funds. So this product is powered through the Elliptic Entity Graph. We're going to be touching a bit on this, but essentially it's like nodes, edges, right? Nodes being blockchain addresses that are labeled or unlabeled, and the edge is essentially the flow of money. And then why this problem is hard? So unlike traditional banking, where everything is known, like all entities are known, in crypto, everything is fuzzy. So whenever we have a customer request, essentially, we have to run thousands of traversals in real time in order to provide insights to the customer, right? And on top of that, we have 50 different blockchains with different characteristics that we have to integrate into our platform, which makes this problem even harder. The other product we have is the graph visualization product. And this allows, essentially, single-click correlation investigations to uncover illicit activity. This is powered through the Elliptic Entity Graph and the user-facing analytics. And as you can see on the picture, on the left, this graph, essentially, the user can see the UI, right? The nodes and the edges. We can see in pink, this is like an unlabeled address. We don't have information. We don't have a label for that address. But in the middle, we have a sanction entity, right? Like, we receive this label, this intelligence. We show it into the UI, and the user is able to understand more what's happening. The other component that is very important for the graph visualization product is the user-facing analytics. And essentially, this is a tab we have on the right that is able to provide more insights to a customer. And this is key to have an effective investigation for the customers. Key insights that we provide could be given an address, right, a blockchain address, we are able to provide a list of the different transactions that this address has been part of. We are also able to provide a total incoming value that a certain address has received, the total outgoing value that a certain address has ever sent. And why is this a problem, a big problem? User-facing analytics, it's a hard problem because essentially it requires a lot of query filters, right? As you can see on the tab on the right, we have 1, 2, 3, 4, I don't know how many tabs we have, but every tab that we have, it requires different query filters, and not only that, but these query filters are querying the history of all of blockchains that we support in the platform. So 50 different blockchains, Bitcoin, Ethereum, 50 more, 47 more, and all the history of it. And I think it's around 300 terabytes or something like that in total that we have to query in real time and provide these insights to our customers. So just to give a bit of history of Elliptic Platform and the different evolution of it. We start very humble, just supporting Bitcoin, Ethereum. We were having Neo4j for a graph database. We were running traversals on it. Everything was in batch. We were running batch processes, very expensive ones. to dump all this data into Neo4j. And essentially, we had one Neo4j for every blockchain, which made it very complicated to scale, essentially. So as we started to grow and integrate more blockchains into our platform, this was a challenge, right? And that's when in 2021, we put a lot of effort to build the scalable platform, essentially, that was blockchain agnostic, powered by DynamoDB and Lambda, that could power both the entity graph and the user-facing analytics. So you can see here the diagram, right? The architecture diagram, where data ingestion, essentially, it's blockchain data coming from it's in Kinesis, but essentially we have a team, dedicated team, that they are the domain experts for blockchain, and they push all this data into Kinesis. And this comes in real time. We also have the intelligence, right? We have seen in the UI before, where on the addresses, we might have intelligence on it, and we put a label, right? And this intelligence is essentially computed from our intelligence team to do that, right? We use ML to do that as well. And just to focus on the top part of the architecture, right? We see the entity graph. We see the compute essentially is Lambda. From AWS, we have the entity graph stored in DynamoDB. And then the graph traversal is done in a in-house graph server hosted in Kubernetes, where every time we have a customer request, again, we run the thousands of traversals to provide real-time insights in less than a second to our customers. And this powers the risk detection engine, essentially. The bottom part of the architecture, we see the user-facing analytics. It also reads the blockchain data and intelligence, and stores these tables into DynamoDB. And again, it's powered through the in-house graph server and powers the graph visualization products that we have talked about. This is the real-time platform. It's important to say as well that the first time we have to integrate a new blockchain, we have to do it, we did it in a Spark, essentially. So we use Spark to read all blockchain history, and we dump all this data into DynamoDB. But we start to see that soon that the user-facing analytics had a lot of challenges. And one of them is what I mentioned before. It has a lot of tabs. It required a lot of query filters. And suddenly we realized that this one was scalable, right? We had to add one index, one table, every time we wanted to power a new feature on user-facing analytics. Compute limitations. So we're trying to do a big data job inside Lambda, and this was clearly not ideal. So this prevented us from expanding. And heavy maintenance architecture. We were maintaining Spark logic to initialize and backfill all the blockchain data. So this required some custom, logic and code. As well, we were hosting all the real-time logic in Lambda, functional programming. So our engineers had to, maintain 2 different repos, super different. And again, this was very complex. Next milestone in our platform that I want to highlight is 2023, we fully migrated to Databricks, giving us access to Databricks ecosystem. And then next thing important to highlight is 2023, blockchain transactions start hitting record high. And just to show some numbers here, so we can see here the graph, which is it grows from, it's very small, but it grows considerably incredible, from 2023 to 2025. And you can see that in January 2023, we ingested 1 billion transactions. 2 years later, we tripled that. The number of blockchains supported as well, we doubled that. And the number of structured data into a platform, again, we tripled that. So our platform started to see more blockchain data, the costs were rising, and we had to do something. Something to highlight here as well from the Databricks timeline is that 2023 SQL Warehouse REST API goes public preview, and this is going to be useful for context for the next slides. And then we had to do something. We could not expand user-facing analytics. We were blocked through the compute, through the cost, and we decided to do something, right? We didn't have much engineering capacity back then, and that's why we kind of do a hack. I don't want to say a hack, but we had to do something quick, right? And that's why you can see that we didn't touch the main architecture, but with dotted lines, we added extra computation, extra storage, and extra read computation to power user-facing analytics, right? So this quickly allowed us to expand the functionalities on user-facing analytics without committing much engineering resource, essentially, and again, allowing us to expand, right? So just to touch on that, we just essentially stream all the data coming from Dynamo using sparse streaming, storing it into Delta, and then querying it through SQL Warehouse. And then the last milestone I want to highlight today of this evolution is that last move that we have seen, like these dotted lines, adding Dynamo and adding Delta, we did in a reactive way. We had to expand, we had to do something. But then when we had time, when we had the buffer, when we had the engineering resources, we decided, okay, let's do something. Let's build the platform. Let's build a platform fully powered by structured streaming. We would ingest directly everything into Delta, powered by SQL Warehouse, and this would power directly the user-facing analytics for our graph visualization. Worth mentioning as well, everything was governed by Unity Catalog, and that's pretty much the architecture we have nowadays. So key wins of this architecture: we have streamlined development. We have Spark powering both batch and streaming, right? We have better data governance right now with Unity Catalog, giving better access controls to our jobs, to our data as well. We have scalable compute. So now we don't have the problems with Lambda. With structured streaming, we can horizontally scale. We can horizontally scale as well the SQL Warehouse to query your data in Delta. And yeah, that's pretty much it from the key wins. And now I'm going to be passing to Matt, who's going to be essentially touching on the key components from Databricks that have enabled user-facing analytics for us. Over to you, Matt.
Thank you, Ferran. So yeah, as Ferran was saying, I'm going to be walking through the different components that we managed to work towards in order to adopt Databricks features, but also some of the thought process that went into deciding how we could actually make this scale. The first thing I'm going to talk about is about the SQL Warehouse, which was a critical part of Ferran's architecture. And a lot of the challenges that SQL warehouses have in general are the fact that most of the times the cost of the product itself tends to be 25% of the overall cost that you have with the entire platform. And that is because you have to manage your infrastructure, you need to manage the startup delays on running up a SQL warehouse, idle time when it's not being used, things like governance, maintaining reliability, and these, like many more things. But the main challenge that Elliptic had in terms of capacity was that they weren't dedicating time to actually building up the use cases, but instead trying to manage the existing system, which was not scaling. So some of the things that serverless SQL enabled Elliptic was the fact that one of the things that Ferran mentioned was which was the REST API that allowed them to communicate with the SQL warehouse using programming language without using directly the SQL statement there. But also it allowed them to iterate way faster. And the reason they could iterate faster is because when they're using serverless, the startup times for the warehouses themselves tend to be in the seconds, which means that you could iterate, run queries, turn it off without incurring a significant cost. And this also increases productivity as well as lowering the TCO, as you don't need to manage the infrastructure any longer. So we have the SQL warehouse, but it's only going to be as good as we design the data layout. And we're talking about terabyte level tables, and as Ferran is saying, this is only going to grow over time, so we need to be careful and think very well how we're going to design that. So here we have an example of a query pattern that Elliptic has. They have many query patterns that in their different use cases, but this is one of them, where we have addresses which are a way to identify different wallets in crypto transactions, and they want to find out for this specific wallet what transactions has it participated in, and how being the USD value higher than 2,000. On the right-hand side, we have an example of what that could look like from a JSON perspective. And having this query pattern and the data itself, we have to think about, okay, well, what are the things that you're going to rely on to basically retrieve data from your tables? So for the thought process part, we have a wallet address, which is a key that is very important when querying the data. And we're going to touch a little bit more about this because there's some things about the hashes that aren't ideal for many situations, but in this use case particularly, and in crypto in general, is actually pretty important. The other aspect of it is the USD value, which is also very important, considered as a common filter condition. So we considered the different options that were available, and just to remind you, this was 2 years ago, 2023, when we started the partnership and how we can actually scale with Databricks. So the options that we had available was Hive-style partitioning, Z ordering, and liquid clustering, which back then was in public preview. And for that reason, we ended up not using it because there were some limitations at the time around bigger tables. So we basically said, like, let's make sure we use something that we know is going to work. And that way we avoid getting burned by any of those limitations. So we went for Hive-style partitioning combined with Z ordering. And this is a very common combination when working with big tables because they complement each other. So we have Hive-style partitioning, which is really good for those low cardinality columns, and Z ordering, which handles very well those high cardinality columns, such as USD value and things like that. So for the Hive-style partitioning, because the read of the wallets themselves were so potent, we had to find a way to simplify how we basically lower the cardinality of the wallet so that we could basically partition it more efficiently. And for that, we had an algorithm that will help us basically truncate the address to specific characters so that we could spread the load of the data more evenly. And that also allowed us to do partition pruning within Databricks. With Z ordering, we chose to use USD value for it, which allows us to basically cluster the data more efficiently in terms of the USD value column, which also allows us to do file pruning. Still, having gone through this, and I'm actually going to talk a little bit more on the optimization part, we still had a lot of skew, where some partitions will have as low as 18 megabytes, and some other partitions up to 130 gigabytes. And that is really, really bad in terms of performance for queries that may basically read from those two. So how did we get the data from our source to our SQL warehouses and basically build that data layout throughout that journey? So as Farhan mentioned, we have the Kinesis connector. And this Kinesis connector is a native connector that we have available within Databricks. And the great thing about it is that it's parallelized by shards, but also it's managed for you. Having said this, there are two main threads that you need to think about when working with this connector, which is the record fetch buffer and batch execution. The reason I'm mentioning this is because these play an important role in managing how much data you flow through your system. And that is, Farhan is actually going to talk a little bit more about that, but it plays an important role in making sure you give a stability to your pipeline, and you avoid getting spikes of data that may cause the pipeline to lag. Moving to Delta Lake, the great thing about Delta Lake is that it's a format that allows for streaming and batch, which is incredibly powerful. And another great feature that it has is that it guarantees exactly once, which means that you can, once you solve duplication, if you have any duplication at the source, once it's in Delta Lake, you don't need to think about potential duplicates there. As I mentioned with Kinesis, here we have as well two knobs that are very, very important to consider while building pipelines and streaming that allow you to throttle how much data you read from your tables. And it may sound counterintuitive, where you're saying, like, why am I slowing down when I need to go faster? But you'll find later why that actually makes sense. So having said this, we've built the pipeline, and we would like to say that we were done. But the reality of the situation was that there were a lot of issues that we still needed to solve based on our original design. And also, because the time frame of this, a lot of features were released from Databricks. Liquid clustering actually went GA, which was one of the things we started revisiting. Starting with the existing situation that we had. We had Hive-style partitioning and Z ordering, like I mentioned before. And this is a visualization of how that could look like, where partitioning, as you may know, it offers physical boundaries within different folders to separate the data. And liquid and Z ordering allows clustering between multiple ranges of USD value and basically combine the data into those same files. This improves the read times, but it actually has some issues when treating it in this situation. The main issues that you have here is the fact that partitioning has physical boundaries. And that causes you to have skew. I mentioned before that we have some folders that have around 80 megabytes, other ones will have 130 gigabytes. Well, that actually provides a little bit of inconsistent performance in your pipelines. Another issue that you have with Z ordering specifically is that it causes some issues where you need to optimize and need to think in terms of maintenance because you have to specify what you want to optimize on. And another important factor is that this is static. Once you decide how you're going to do the Hive-style partitioning, you can't change the columns that you've chosen without rewriting the entire table. And now we're talking about terabyte level tables, so rewriting every time you want to change it is not good. One other issue that we encountered with Elliptic was concurrency. And with Hive-style partitioning and Z ordering, you get file level concurrency. What that means is that if you have two pipelines that are interacting with the same table, if those two pipelines touch the same file, it's going to cause one of those pipelines to fail. This is a situation that we had in Elliptic, so that is a factor when we decided to revisit this as well. So let's talk about liquid clustering. You can see the visualization is a little bit different, and the reason it's different is because with liquid clustering, you no longer have physical boundaries for your data. The algorithm itself that optimizes it will decide how to best cluster the data between the different columns that you've chosen. It also makes it way simpler, where you now choose address and USD value for liquid clustering. You don't need to think about cardinality any longer. So if you have a low cardinality, high cardinality column, it doesn't really matter. What matters most is that you follow your query patterns. So before we mentioned that we're using wallet and USD value, well, we liquid cluster by those. The great thing about it as well is dynamic. If your query patterns change or you have new queries that use different columns, you can actually add the new column, optimize, good to go. Another great implementation from liquid clustering is the fact that it offers row-level concurrency. And that takes it a level further where you can actually interact with the same file, but as long as you're not touching the same row groups within the Parquet file, you're not going to get conflicts, which reduces the hits when you're working with the same files by a significant margin. The other thing that this solves is the fact that you no longer have skew. Because you're combining data between all these different columns and you don't have any physical boundaries, you now bring a little bit more stability in terms of how you're going to get performance in your tables as well. So now that we've solved the data layout for these tables, let's actually talk about other optimizations that we considered when we revisited this. And some of you may have already heard about deletion vectors. I'm going to briefly explain what they are and why they actually were created. So you may be aware that Parquet is an append-only format, and that has some limitations, especially in the new way of working with lakehouses, where we not only add data, but we actually need to edit it or delete it. And being Parquet an append-only format, that means that if you ever edit or delete, you're going to have to rewrite the entire file. In this situation, we're doing streaming, so we are continuously rewriting these files, which is, again, inefficient. What deletion vectors does is actually create a binary file that tracks the deletes that are happening within the Parquet. And the engine itself will decide and amortize those deletion vectors to choose when is the right time to actually rewrite, because it's going to be worth doing that compared to just adding it to the deletion vector. And by doing this, we now improve dramatically the performance of doing merges, because we no longer have to basically rewrite an entire file. We can simply create a new file and tag the deleted vectors on the older Parquet. Now that we're talking as well about merge operations that are happening within the pipeline itself, this is something that I've encountered many, many times with customers. And I'm not sure if people are very familiar with static file pruning or dynamic file pruning. Is anybody familiar with it? Not many people, which is unfortunate. So I'm going to actually explain why this is an issue and why you should be considering it when you're building structured streaming pipelines. Static file pruning is a way of specifying in your merge operations how you want the target table to behave. You're specifying, when you're doing a merge operation, that you want to limit the data that you're going to do the merge operation on. The reason you need to do this is because when you're doing a merge operation, where you're not specifying the filtering, the static filters that you want to use, like we're doing an example on the left, where we're specifying the timestamp that we care about, the scan operation on the target table will basically read the entirety of it. Meaning, if you have a 150 terabyte table, you're going to read the entirety of the 150 terabyte table to figure out what exactly you want to join on. many customers don't consider this when they're building their pipelines, and they start complaining that the performance of it is actually lagging significantly, which is something that you should be considering if you're doing it. And in this example, that's the way that we approached it as well within Elliptic. Moving on to the right-hand side, where you have dynamic file pruning, this is actually an improvement that comes with using Photon, which is a native engine with Databricks that you can use, which makes the problems, it solves the problem basically. So instead of you having to think about doing file pruning yourself, where you have to decide what columns you're going to do the filtering on the target table, you simply do a merge operation, which is pretty simple. You simply say, like, I want to join by hash, and in this case, I want to join by Unix timestamp. And under the hood, it will actually do the logic that you would have to do on the left-hand side. So it will basically be like, OK, this is the microbatch that you want to join on. I'm going to pass the columns that I'm going to join on to the target table. And the target table will use that to basically do a filter and only bring in the data that you're going to need to do that merge operation. So having talked about this, Ferran is actually going to talk a little bit further about how they thought about the data layout in terms of columns to optimize the dynamic file pruning of the tables.
Thanks, Matthew. So what I want to explain now is a bit how important it is to choose a good clustering key. And for that, we're going to base, with the example on the right, you can see similar JSON that Matthew showed before, where we have Unix timestamp, the network is essentially the blockchain, height is the block height of the blockchain, transaction hash, random hash. From is the sender, to is the receiver, asset is intuitive already, and USD value is the amount of money that the sender has sent to the receiver, right? And essentially, what we want to do here is store these transactions in the transactions table, right? This transactions table is going to be around 15 terabytes data, right? We want to test how we can improve merging this micro batching from structured streaming to this 15 terabytes transactions table. The transactions table is a liquid cluster table. We are using a cluster, 5 workers, I3 to wake large. As Matthew said, we're going to be trying to use dynamic file pruning. So every cluster key that we have to make sure it's passing on the merge key. And in this case, the merge key is the transaction hash, network, and Unix timestamp, which are the fields that uniquely identify a transaction. So the first result, or the first example that we're going to give is just setting the transaction hash as a cluster key, right? Which is required for the read performance, right? We have this table, we have to query it through the hash, so we cannot change that. And by only putting the transaction hash, we can see that the number of files pruned is nothing, right? We prune less than 1% of the files during merge, and this results in a very slow merge, right? This results more than 20 minutes per microbatch. But what happens if we add Unix timestamp into the cluster key? Unix timestamp is an order column, right? And the results are amazing. You can see here the number of files prunes goes from less than 1% and more than 99%, making the merge into Delta table, right? Into a 15 terabyte Delta table, making this merge is less than 1 minute, which is incredible results. That's it in terms of optimizations. We're going to show a bit best practices that we have in our architecture. In order to do that, we have to do a bit of zoom in into the architecture we were touching at the very end, right? The architecture we have currently. And that's pretty much the architecture that we have currently in our platform, zoomed in. Right? We can see here we have 2 streaming jobs, right? The first one is the transaction stream, reading from 2 sources. The first one is blockchain data coming in and streaming, right? We have 50 different kinesis reading, like we have all the data in kinesis, 50 different kinesis, 1 for every blockchain. And this is being read by the transaction stream. And this stream is reading as well from another table. We can see the backfill table. What is this backfill table? In this backfill table, every time we have to integrate a new blockchain into the platform, we just batch all of this data into this table. And essentially, it's just in one commit, we just have a lot of data, right? And then this stream is writing into a transactions table, right? This 15 terabytes table I mentioned before. And we write it there just to accomplish idempotency. We don't want to process the same transaction twice. And just by writing it there, we just ensure like all the transactions are just processed once. And downstream of that, we have the user-facing analytics stream, which is reading the CDF from this table, and it's also reading the CDF from another table, in this case, the intelligence table. In this intelligence table, similar as in the backfill, right, or Intel team, they batch all of the Intel, the new assertions, the new intelligence that they have created through ML, manually, whatever, into this table, and in batch, right? And this user-facing analytics stream reads both sources, right, and writes into 4 different aggregation tables that are needed for our user-facing analytics. And you can see here the scale, more or less, the size of each table. So the first best practice that we had to adopt is atomic writes, especially on the user-facing analytics stream, right? What happens if we do the first 2 writes on the first 2 tables, and we have a failure after that, right? Before writing to the transactions table 3. We would not have data completeness, right? We have some tables having some data, other tables having another data, and then if we just restart the micro batch, we would add into the transactions table 1 and transactions table 2 duplicate data, right? We have deltas, we are adding deltas. Essentially, we would end up with, like double counting. So in order to do that, we implemented some strategies to, whenever we have a failure, we're going to do some retries. We're going to discard all the micro batch into S3 to process it later and to quarantine it. And then we're going to roll back transaction table 1, the aggregation table 2 and 1 with the delta rollback. And that ensures we have data completeness. The other best practice we adopted here is graceful stopping. Right now, when you have a sparse streaming job and you have to stop it and start it just to do maintenance and change the HR, for example, we use Scala. We don't know at what point in time this stream is. And essentially, we had to, using sparse listeners, just detect whenever the micro batch has finished, and we just use sparse context, just stop the sparse session, and ensure like we always write whenever all the writing into different table has finished. We don't stop the streaming midway. The other best practice we have adopted is limiting input rate, as Matthew has mentioned, using these 2 configurations. And I'm going to just do a bit of deep dive into this one, right? And sorry, let me go back 1 sec. And before doing this deep dive, I'm going to give an example of what happens when we do an intelligence load, right? When we do an intelligence load into the intelligence table, and especially when we do a batch of, let's say, 3 gigabytes of 10 gigabytes, and we don't want the stream to be lagging, right? The stream is configured to process in a certain capacity, and we don't want a big batch to cause lag to the other tables. So this is an example of the Intel table from the Unity catalog, essentially. And you can see an example of an Intel load of 195 files and 3.5 gigabyte size. So by using the max bytes per trigger, this is very interesting, we have seen that thanks to Delta, this big batch of 3.5 gigabytes is split into 3 small chunks, well, 3 or more, but it's split into small chunks. And for those you are not familiar with the checkpointing offsets, right? Whenever we have a streaming job running in structured streaming or Databricks, whatever, we have this checkpointing folder. We have this offsets folder that keeps track of what point in time we're reading from the Delta table. And on the right, you can see 3 different micro batches. In this case, it's micro batch 62, 63, and 64. And you can see it's a bit little, but you can see 2 reservoir versions. The first reservoir version is the version of the transactions Delta table that the user-facing analytics stream is reading. And the second version is the version of the intelligence table that, again, the user-facing analytics stream is reading. And you can see that across all 3 different micro batches, the index is exactly the same, meaning that we are processing this big batch into smaller chunks, not causing any lag when writing to different tables. So that's pretty much it on best practices. Key takeaways of this talk. So we have seen that we had to do kind of a hack in 2023 when blockchains were rising. We had to add this streaming pipeline writing to Delta. We have built a scalable platform proactively and ensuring we are ready for the next crypto wave. We know it's going to happen, and we don't want to not have a platform that can process data at the scale. Databricks has allowed us to focus more on our domain. So components like SQL Warehouse, components like dynamic for pruning, even Spark. When we trigger Spark job, we don't configure the memory. We just rely on Databricks to do that. And we have seen that it's way better to do that than just writing the memory, the driver. You forget about this. Just use Spark, and Databricks will figure out that for you. And this allows us to focus more on our domain, on what we care, which is crypto, and data processing with crypto. We have seen that in a lakehouse architecture, we can power near real-time features. And probably this was not possible 10 years ago with Parquet. But now, with all the components with Databricks ecosystem, this is possible. And we have seen it with the user-facing analytics. And lastly, but not last, data sharing. I haven't mentioned anything about data sharing in this presentation, but thanks to Unity Catalog, apart from the governance, this has allowed us to seamlessly sharing data thanks to delta sharing. And I think that's pretty much it for today. Thank you for attending. We are going to have happy to attend questions downstage. So yeah.
Thank you.
Thank you.